Great. Hi everyone, welcome again to the AWM Pitt Grad seminar. Our second speaker is Agnese Mantione. She is a PhD student from University of Münster, Germany. Her talk today on Introduction to G2 Holonomy. You can proceed now.
Okay, yeah, thank you very much. Can you see the screen?
Yes.
Yes. Okay, so actually today I wanted to talk about the topic of my postdoc since I recently defended my thesis and now I'm getting into a new topic. So I don't have any result yet because I just started learning about it and I thought it would be nice to share what I learned with you. Yeah, I will start giving the idea of what holonomy is and then moving into the G2 holonomy and giving some results that involve G2 holonomy manifolds. Okay, so in general, when we talk about holonomy, we can have this picture in mind. So one can take, for example, the sphere and ask how moving the tangent space along a curve, along a loop actually, how does transform like vectors of the tangent space. So in this picture, um, you can see that these green two vectors, once we move the tangent space along this loop, are sent to another tuple of vectors. And this can be described by a linear transformation of R2. But in general, there's a generalization of this concept, and also to make it more precise, we need the notion of a derivation for general vector bundles over a manifold, so not necessarily the tangent bundle. So to do that, we need to define what a connection is. So on a vector bundle of finite rank K over R, a connection, as I said before, like would kind of simulate a derivation along for sections of the vector bundle along vectors of the tangent space, and it has to set it's a linear map, and it has to satisfy these equation. Moreover, as I said before, we are interested in the derivation along vectors of our tangent space. And so we denote this in the following way. And yeah, and also with respect to smooth functions on the manifold, then the derivation somehow preserves what for the usual derivation on Rn would be the derivation of a product of a smooth function for a vector field. Okay, so with this in mind, we can define what a parallel transport, what a parallel section is. So in the picture that I showed at the beginning, we took a loop on our manifold, but in general, one can look at a smooth curve with initial point x and final point y, and take the pullback bundle. And at this point, for any section of the pullback bundle, we define the notion of parallel. So a section will be called parallel if it satisfies an ordinary differential equation that involves the tangent vector at every point of the curve. And this is an ODE. And for the theory of ODE, given an initial value, there is a unique solution to the differential equation. So this unique solution we denote by S, and then we define phi gamma of the chosen E to be the value of this S in 1. This would be an element of the fiber of the bundle in Y, and then one can, so this process gives us a well-defined linear map from the fiber at the point X to the fiber at the point Y, which is called parallel transport map. In particular, this map, this map would be invertible because one can interpret the inverse of a curve as the curve percurred in the opposite direction, so using this notation. And curves can also be composed. So we have that if, for example, we take a loop, then the parallel transport along a loop has an inverse, which is the parallel transport of the loop taken with the opposite direction. So starting from y and going to x, but in this case, because it's a loop, so instead of taking in this direction, we go the other way around. And then we get a linear transformation of the fiber at x. So finally, with all this information, we can define the holonomy group. So the holonomy group refers to a chosen connection. And to begin with, we define it at the chosen point of our manifold. It is the subgroup of linear transformations on the fiber of X of parallel transport maps for loops at the point. But somehow this definition can be made independent on the choice of our point. And this means that if we have a connected manifold, any 2 points can be connected via a piecewise smooth curve. And so because of that, and thanks to the property that we had before, we have this rule of composition. And so if we start with a loop at x, then we can consider the parallel transport along gamma and along the inverse of gamma. And then we get an element in the holonomy of at the point y. And so we see that the two holonomy groups are in fact conjugate. And so up to conjugation inside the general linear group, then the holonomy group is kind of unique, independent, on the point. So we just use this notation without specifying a point because we will always work with connected manifolds. Moreover, a nice property for the holonomy group is that it is a connected Lie subgroup if the manifold is simply connected. And if the manifold is not simply connected, we can still get a connected Lie subgroup, provided that we take the components of the identity. So we just take parallel transport maps of loops that are null homotopic. Okay, so I finally gave this definition of holonomy, but what is the interpretation? What does it mean in practice? Okay, so holonomy is strictly related to G2 structures. So the idea is that if we have a certain holonomy group, then we will be able to reduce the structure group of the frame bundle of our manifold to a G structure on our manifold, which means a principal subbundle of the frame bundle with fiber G. So in other words, we start with a k-dimensional manifold, and then we have that the frame bundle is principal bundle of fiber GLKR. So once we choose a Lie subgroup of this group, then a G structure is defined to be a principal G subbundle of the frame bundle. For an example of a G structure is like an O1 structure, which corresponds to a Riemannian metric. So for a Riemannian manifold, we can define principal sub-bundle of the frame bundle by only taking frames that are orthonormal with respect to the metric G. And then what we get is an O1 subbundle. So there's this identification of Riemannian metrics and O1 structures. If, for example, we ask for something more, like say orientation, then we will ask for an SON bundle. Okay, but again, I didn't say it yet. This is related to holonomy by the following relation. So we say that a G structure on M exists if and only if, so also torsion-free, but somehow this will come in a moment. I just want to focus on this bijection. So G structures correspond to connections with holonomy contained in G. Okay, then often we need the notion of torsion-free to make sense of this, but I think we don't have really a lot of time to get into this. Somehow there's a notion of connection also in principal bundles. And imagine that this means that the torsion of that principal bundle is 0, where it refers to the connection identified by this principal bundle. And on the other side here, to have to be torsion-free for a connection on a vector bundle, it means that it satisfies this equality for every 2 vectors in the tangent bundle. Okay, so now I want to mention a few more examples of G structures. So before we said what a Riemannian metric is, then what an orientation on a Riemannian manifold is. And well, we also probably heard about complex manifolds. And complex manifolds are manifolds with a torsion-free GLMC structure. Symplectic manifolds have a torsion-free SPEMR structure, and Kähler manifolds have an torsion-free UM structure. And then finally, here I wrote G2 manifolds, which maybe is a more mysterious thing, but this is what we will be talking later on. So G2 manifolds are manifolds that have a torsion-free G2 structure, and I will explain what this means soon. But somehow I just added it because I think we will talk about this later. So, okay. So once one learns about holonomy and this connection with structures, like an interesting question to ask is what connection there is between, what groups appear as holonomic groups. And in general is a very wide question. So we could specify some conditions to get some restrictions on the possibilities. So the first thing to do is to impose torsion-free conditions, also because we have seen that in order to have certain nice structures, we need the torsion-freeness. And imposing torsion-free conditions gives 2 identities called Bianchi identities. And so our connection needs to satisfy these 2 conditions, which makes it simpler to work with. And also we can just pick a Riemannian metric, and we look at the holonomy of G, where we mean the holonomy of the Levi-Civita connection, which is uniquely determined starting from G. So we will look at this type of connections, and also we can focus on simply connected spaces, because as I said before, for simply connected spaces, then the holonomy group is a connected Lie subgroup of the general linear group of Rk, where K is the rank of the manifold. The dimension of the manifold, or the rank of the vector bundle, which in this case will be the tangent bundle. And next we will also just work with irreducible manifolds, which mean that our manifolds cannot be of a product type, because if that were the case, then the holonomy will also decompose as a product type. Okay, so the first positive classification of holonomic groups appears for symmetric spaces. So symmetric spaces basically are homogeneous spaces, and because they have this structure of being homogeneous, which means they can be written as a quotient of a connected Lie group and a close connected Lie group, then the quotient group here would represent the holonomy. And so classifying holonomic groups for these spaces is equivalent to classifying Lie groups, which was done by Cartan. So the problem is somehow solved for symmetric spaces. So, well, I just mentioned here the definition of what a symmetric space is, which, so it's a Riemannian manifold is said to be symmetric if for every point of the manifold one finds an isometry that is also an involution and has the point chosen at the beginning as an isolated fixed point. And one and then we would see that, I mean, one can show that this G, in fact, is a group generated by these isometries. And H is the group, the subgroup that fixes a point. Okay, so some examples of symmetric spaces that probably everyone knows about are the Euclidean space with the standard Euclidean metric, the complex space, and for instance, the complex projective space, but also the hyperbolic space, and in general, just, yeah, homogeneous spaces. Okay, so next, the harder the situation gets more difficult once we take away this symmetry condition. And Berger furnished a classification, or somehow a list actually, of groups that could be the holonomy of non-symmetric spaces. But when he first introduced this list, it wasn't clear whether all of them actually appeared as the holonomy of a non-symmetric Riemannian manifold. So in principle, yes, like the holonomy has to be one of the following, but some of these groups could be excluded. So the first part of the list, in fact, kind of has a connection to algebraic geometry. So there are nice examples of manifolds that have this holonomy. For example, yes, as we talked before, in general, well, if we have an orientation for a Riemannian metric, then we also have an SO1 structure, and so the holonomy will be here. And for a Kähler manifold, the holonomy is contained in UM, and so on. So with Calabi-Yau, we also have like, well, all of these have somehow an example which is visible, which is like a global, so has global holonomy as these groups. But for the second part of the list, so for G2 and spin 7, the situation is harder because algebraic geometry doesn't really help. And to study this, one should look locally and also study this torsion-free condition more deeply. So it's kind of harder. Somehow, though, it's still possible to find manifolds with this holonomy. And so maybe because I want to focus on G2, let me talk about G2 first. And then I would say what is known for this group. Okay, so G2 is often defined as the automorphism group of the imaginary part of the octonions. And well, it can be shown that is a simple group of dimension 14 by using the fact that it acts on the 6-dimensional sphere transitively with stabilizer SU3. But another description of G2 is as the subgroup of the general linear group on R7 that preserves a specific chosen 3 form, which I wrote down here. And analogously, well, then it will also preserve the Hodge dual to this form. Okay, so well, maybe let's also motivate a little bit why should we even care about these G2 manifolds or their existence. So a reason to care that comes from geometry is that imposing the condition of holonomy G2, one gets some constraints in the curvature, which imply Ricci flatness. And another possible reason to care for G2 manifolds is that they work nicely in physics, specifically in string theory. Okay, so if these two reasons for you are enough, then we can ask, does a manifold with that holonomy exist? And the problem was solved for the first time by Bryant and Salomon, that offered an example of a complete metric with G2 holonomy. However, the manifold that they constructed was not compact. The first example of compact manifold with G2 holonomy was given by Joyce. And what he used was he took this space, and then he resolved the singularities, and he was able to match the 3 pieces with the specific metrics, and then he showed that the torsion was 0, and then the holonomy had to be G2. Okay, but other examples of manifolds, I mean, with the G2 holonomy then have been constructed afterwards. And for instance, one can construct infinitely many G2 holonomy manifolds by taking twisted connected sums of products of an SU3 manifold and a circle. So what happens is that one can glue these two copies along the boundary, twisting the components. So if this V is of this type, where K3 is the like K3 surface, then one would have that basically one will want to glue V plus times, so the boundary of this with the boundary of this. And so we will get S1 times K3 times S1 to S1 times another copy of K3 times S1. And this identification can be given by many different diffeomorphic many different diffeomorphisms, and so this will give many manifolds. But it's unclear to begin with whether these manifolds can be distinguished maybe up to diffeomorphism or up to homotopy. And this is the classification question to which we will come in a moment. So maybe let's go back to this G2 interpretation. So we saw that G2 structures correspond to manifolds with the holonomy G2, provided that we are taking torsion free. But if we don't take torsion free, if we don't ask for torsion freeness, then we are kind of relaxing a little bit the condition. And so we have a more general, so we have hope to actually find more examples. And because of the different, so the second description of G2 holonomy that I gave before, sorry, of the G2 space as the stabilizer of that 3 form, then we can also define a G2 structure, not just as the reduction of the structure group of the frame bundle, so not only as a principal bundle, but also more geometrically as a tuple of a 3 form and a metric. And this 3 form is what is called to be a positive 3 form. And for a 3 form to be positive, it means that once we restrict to a tangent, so the fiber over a point P, then this form has, for this form, there is an oriented isomorphism between the tangent plane and R7 that identifies the form with phi 0 that we defined before on R7. Okay, and at this point, well, as we said before, torsion-free G2 structures correspond to holonomy in G2, but what was known and then has been shown by Bryant is that this is also equivalent to asking for the form to be closed and co-closed. However, here, this is a nonlinear equation because this star is defined from the metric, which is again depends on phi. So basically from the form, we can define a metric. And so here we have a nonlinear equation. And also here, because again, the connection is determined by the metric, which itself is determined by the form. Okay, so here somehow this explains how complicated it is to actually have a torsion-free G2 structure. But again, one can just look at G2 structures and, for example, try to classify only G2 structures. So tuples of manifold with a positive 3 form. And well, sometimes, well, one would hope to have some results for torsion free, or maybe weaken a little bit and just ask for co-closed forms. So, well, I guess what we could ask is, what is the topology, for example, of the space of the G2 of the G2 structures on a manifold? or the moduli space. So here I wrote down some interesting results that I think are worth mentioning. So the first one is by Joyce. And what Joyce was able to prove was that the moduli space, where here we take the component of diffeomorphisms that, so the diffeomorphisms in the component of the identity. So this moduli space was proven to be a non-singular manifold of dimension given by the rank of the third cohomology. And then I think other two results that I would like to mention are the fact that also up to homotopy, we can distinguish G2 structures. So now here, this is just G2 structures and not torsion-free. But yes, it has been shown that there are infinitely many G2 structures up to homotopy. And once one mods out the diffeomorphism group, there are still, well, the cardinality of the group is still non-trivial. So, for example, it can be shown that it's at least 24, and for specific manifolds, it's equal to 24. And the invariant here constructed by Crowley and Nordstrom is, interestingly, this is a topological invariant, but in a recent paper, together with Goethe, they proved that there's a refinement of this invariant, which takes values in the integers and can be defined analytically, which is often the case that certain topological invariants are also analytic or have an analytic interpretation. But it's very interesting because thanks to the result, they're able to show that two G2 holonomy manifolds are actually in different components. So not just the G2 structures, but also here by adding torsion-free. Okay, so I think this is all I wanted to talk about today. And yeah, thank you very much.
Thank you so much for the talk.